Hi everyone, I am Abdul-Rauf Nuhu, the first author of this work, and our work is titled A Niching Framework Based on Fitness Proportionate Sharing for Multi-Objective Genetic Algorithm, MOGA-FPS. This work is motivated with the fact that many engineering problems involve multiple conflicting objectives and are normally framed as multi-objective optimization problems. Evolutionary algorithms offer promising solutions to these optimization problems by finding a set of optimal solutions. By so doing, offer decision makers with many options. However, there are challenges associated with some of these evolutionary approaches. For example, MOGA, multi-objective genetic algorithm, struggles to preserve diversity when combined with allied preserving strategies. The niching framework or the niching method used in this approach or framework do not guarantee the removal of crowded non-dominated solutions when the population set become overwhelmed with many of these non-dominated individuals. Selection of the niching parameter or the niche radius in different benchmark problems is also another challenge. Given these challenges, our objective is to develop a niching framework to mitigate the diversity preservation drawbacks of the existing evolutionary multi-objective algorithm. For the proposed approach, our primary contribution is the niching framework, which is based on fitness proportionate sharing. For fitness proportionate sharing, sharing is done based on individual fitness. So after we identify the niches in the population set, for each of the niche in the population set, we maintain the original fitness of the niche master. Niche master in our setting is the individual with the smallest index in each niche and derate the fitness of the other individual with the corresponding niche count. Algorithm 1 gives the implementation of our niching framework. For the second contribution in this work, we propose a dynamic strategy to find the niche radius. Algorithm 2 gives an implementation of the niche radius. For this niche radius, we're able to mitigate the challenge 3 pointed out in the challenges section. For the results section, for the test suite, we use bi-objective test functions, which are some of them are shown in the first column of table 1. And for the experimental setup, we considered a population size of 100, a crossover probability of 0.9, and a mutation probability of 1 over n subscript d. N subscript d is the size of the decision variable. For the compared algorithm, we considered NSGA-II, MOGA-XC, a variant of the work implemented in reference 1, and MOGA, the baseline algorithm. For performance metric, we consider spacing. Spacing is an evaluation metric that shows how well and evenly distributed the optimal solutions are on the optimal front. So figure 3 gives the non-dominated solution distribution for ZDT1 and ZDT2 in the last generation using our approach MOGA-FPS and the baseline approach MOGA. For the first row, this shows the solution distribution of our approach, and the second row, this plot shows the solution distribution of the baseline approach MOGA. So if you look at the first plot, you realize that it gives an even and final distribution of solutions as compared to the second row. For the statistical significance of our approach, we use the Wilkinson sign rank test, and the p-value that we adapted or we used was 0.05. And the smaller the spacing value, the better the algorithm. So if you compare all the test functions in here, our approach retained the smaller spacing values, and we highlighted that in red. So to conclude, our approach MOGA-FPS mitigated the drawbacks of the original and shows statistically better performance than some leading edge approaches, and our niching approach adapted to the test functions. For future work, we will focus on more 3 and more objective optimization projects. These are our sample references, and we'd like to thank these bodies for their financial support in this work. Thanks for listening.